All right, this is cis256. Today, I'm going to talk about the assignment for hashing. So at the end of the lecture, I mentioned that there's another way to avoid collision, which is chaining. So basically, the hash table, you can think it as a linear table, or it can be a linked list or a continuous array. Either way, um, suppose you have an internal representation of hashable with array, right? And this array size 11, and you want to insert these numbers into the array. So first things is you need to translate the number using hash function, to hash a number as an input to an index in the array. Now the simplest way is to modular the size of the table, right? So you're guaranteed to map one of the number into one of the location in the array, right? And what if you have collision? So like 77, 44, and 55. If you modular the table size 11, that will give you 0. So these three will map to the same location, and then we call it collision. When this happens, you want to chain them together. So basically 77 is the first to insert, that become the head node of that linked list. And then once you have a 44, you find, oh, there's already a number here. What do? Well, you go through that node and to the next node and put it there. And 55 come along, you have to go 77, oh, there's a node, and his next is 44, this node, and his next is empty, none, so you can insert right there. So every time you have a collision, you just chain them together. Hopefully, the list for each slot are not very long, so you can achieve overall O1 searching time complexity as well. So that's the whole idea. So go back to the homework. So here is the main function. Basically, you should understand the whole, right? So first of all, you have to still have the class bid, which contains these 4 member variables: bid ID, title, font, and amount. Okay, and so when you parse the data from the file, CSV file, which is here, load bids, I already written that for you. Basically, you open that CSV file. The header is basically the name of each columns, right? So you read that as a list, and then you go through each row. Each row is a record. It basically represents a new record of bid. So what you do is do some pre-processing, of course. So this technique is basically clean up the data, right? And then once you've done that for each row, you're gonna assemble a dictionary entry. Dictionary has a key value pair. The keys from the keys row, which is the first row, right? In that CSV, and row is the data. So that zip function will associate each column name with that data, individual data in that row. And at the end of the day, you're gonna stuff in that bid object with ID is the auction ID from the dictionary, entry is dictionary, right? Title is the auction title, and so on and so forth. So that's the whole idea for the parsing data using from the load bits, okay? And then finally, you have to implement the insert method from the hash table to insert that individual bit into that hash table, just like that. So the only difference here is the data itself is a little bit complicated. You need to invent some different hashing function, maybe according to the ID or something, not just the number, okay? But the idea is the same. These are the data. So this is to test your Python skill to basically deal with the real data, okay? And of course, the good habit is catch everything to trial except block. So if any exception occur, you can print out the error message and gracefully quit your program. All right, so that's the load bits. And again, this at log time is basically a wrapper or decorator. What a decorator is basically is a function that takes a function, another function as a parameter. And before you execute that function, you can do something extra before the function. So in this case, log time is basically decorate this function load bits. So to calculate how long it takes for that function to run. So if you look at this function log time, which is here, you can see that it takes the function as a parameter, right? And this wrapper function basically takes all the arguments, which is the position arguments and keyword arguments. The keyword argument, because they have key value pair, so that's like a dictionary. So you have double star, and argument is basically a list. And you take these two arguments, and then you can see I did some time, and I call the function, or the function, whatever passed to me, with all the arguments. I don't care. It's like what you have, I was just call you as is. And then I log another timestamp after the function is done. So all I do is adding these two timestamp here, and then save that into a log, time log.txt file. Excuse me. And that's the record I'm going to save into the log file. And I'm also printing it on the console so you can see it when you run it. And then that's it. So this is a wrapper function or decorator to decorate this function. Okay, so that's the design pattern here. That's one advanced Python techniques called decorator. Okay, so you should be able to understand this. As a matter of fact, in some other libraries like Python's web libraries like Jenkins, Django's, Flask, you will see a lot of this kind of patterns where you can decorate your function with some predefined wrapper, and you don't need to worry about the details because it's being defined for you. All right. So this is that. Okay, go back to this function. So you need to implement load bits, display bits, find, remove, and exit. All right. So these are given that to you. I'm not going to implement all for you. I just want to give you some hint, right? So again, the default size is 179. This is used to calculate hash function. So in hash table class, okay, hash table class, it has two main parameters or member variables. One is the table size, again, and then data. The data basically is like the internal representation of this linked list, right? So you can see this table or list is the data. Okay, so each node in the data is itself can be a linked list. Okay, so that's some combination of data structures. All right, so the data is usually empty, right, with the size, default size. Okay, now you're gonna implement the hash function, given a integer and return an integer. So where the integer come from? Well, the integer come from, you can see hash value according to the hash function, right? So what are you gonna hash? Well, it depends on the ID, right? Where the, so let's see who calls the hash function. Who calls the hash function? The insert method. Let's see. Insert method. Let's go back to the insert method. Here. So the insert method creates a hash key for the given bit using hash function. So the insert method does do the hash function. So basically, in the insert method, you want to get the key from your input. The input is, you call the hash function and get the, let's say your bit, right? So your input is a bit, but not everything a bit, but it's just a bit ID. So I'm going to use the bit ID, okay, which is a number like string. So I need to convert to a actual integer. I can convert that to integer. If you look at the bit ID, if you look at this CSV file, you can see the bit ID, auction ID, right? Is the second column, which is the number, which is but it's read as a string, so you have to convert to a number, and then that's the input, right? So I'll go back to the hash function. if you have an integer, the easiest way to do a hash function is simply modular, right? So we can just very simple return ID modular the table size. Table size it's better to be a prime number because that will give you less collision. Okay, so this is when of course feel free to improve your own hash. The idea is to get less collision, right? So you may have a better idea than I do. So okay. So now let's continue with the insert retrieve the node using the key. So once you get the key, okay, that's the index to this table, and you want to check if there's something. Initially, these are nuns, right? Nothing in it. So you have some condition here. So if no entry found for the key location, so you just insert that, right? Okay. So you get the key, which is the index to that list. So retrieve node using the key. So basically, this line, I'm gonna say key node, which is the node calling that key, is the data. Remember the data with index key the index. So you get that it could be none to begin with because that's the default value, right? So if key node, you can say is none. If key node is none, what do you do? Well, you can you can create a new node, right? So key node is the new node. You create a new node there with the initial bit, and the key of that key node is equal to the key you get calculated. So I have that redundant information here. And don't forget to actually put the actual data to the key node. All right. So insert the key node to that list. Right. So that's empty. Now, if key node is, but its key is none, right? There's no key there. Oh, I can do the other way. There's another way to write it. It's called not this. Not key means the key is not there. Then what? Well, we can assign that node's key to equal to the key and assign key node bid equal to that bid. The structure there is just nothing, no members. So the key node dot next is none because it's the first time you put into that node. There's no linked list, right? That's really in contrast to the collision where there is already a list there. And then finally, you still put the key node into that list. Okay, are we done yet? No. There's another, finally, if there's a collision, right? Finally, collision. Collision means what? Well, go back to the slide. Collision means there's already a number in that. Find the next. So you find the next empty position in the key location, right? That's a linked list. So while the key node is there, next meaning is not none, right? You have a no, then key node is key node. So how to go through a linked list? You just do that, okay? And finally, if you go outside the while loop, that means you find a empty slot, then you just insert it. So you say key node next. So that slot key node is next is none, but now you're gonna put it to node, right? The new node. Okay, so that's take a look at this. This is to find the collision, right? So basically, you find 77, and you say, hey, how about your next? Is next none? No. So you keep going 44, and is 44 none? Yes. Then you just insert 55 after 44. All right. So that's the insertion. Print all is pretty simple, but just a caveat, right? You have to go through all the node in self.data. Okay. And if the node is not none, you only print a non node, right? If it's none, you don't need to print, right? You just print node.bid. Okay. Okay. Not only that, if that node has a next value, so if it's a linked list, then I'm going to assign temp is node.next. You'll do no while temp. So while there's a linked list, I'm going to print that f string, right? Temp, I got temp dot that bit, right? So I'm going to print that, and then maybe some space so you can. I need some arrow so it will be beautifully printed, and then temp equal temp dot next. That's easier, right? So you just go through all the nodes and print out. It's very similar to the searching, right? Key node is Q next. That's how you advance the node linked list in the linked list. Oh, that's it. That's how to print it. So if there is only one value, just print that value. If there's more, you just go through the linked list and print them all. Okay, remove. Remove's a little bit tricky, I guess. Let me talk about it. It's a little bit tricky. Again, you want to search for it, right? You have to search for and remove. If there's nothing there, you don't need to remove at all, right? So again, the key is to have the key, which is calculated from the hash function that you implemented in lib. Again, I'm using bit ID, right? Input is bit. Okay, so you have the key. Now you find the index, right? You see if there's a node in there. So what do? You just look at the internal data structure. Okay, so now I have a key node, right? If key node is not none and key node key is not none, so there's something there. And also, because I'm looking at that bit ID, right? If that node dot bit ID, if that is matching the searching ID, we found it. We're gonna remove it, right? Found the node to be removed. Okay, so how to remove it? Right. Be careful. You cannot simply delete it, right? What if that bid, for example, is 44, but you want to delete 44, but don't want, or maybe it's 77, right? You can't just delete 77, otherwise, these 44 and 55 is gone with it. So you have to kind of like check the next node. If it's none, you can't delete it because that's the last node in a linked list. If it's not none, well, you're gonna remember his previous node and say his next is 44 and delete 77, right? So that's some condition here. So if you have to check if keynode.next is none, if that's the case, you can delete it. So you just delete the key. And if the key is none, then next time people enter that, well, just replace that. So you don't need to delete that node. So the node can be empty and you can just delete the key, right? Or you can delete the node, it doesn't matter. But again, I'm just gonna do very little. If it is not none, what do you do? Well, I'm gonna say it's slot just equal to the keynode dot next. So whatever the next is, in this case, it's 77, right? I'm gonna point you to its next. So 77 is eliminated. All right, just do that. and return. Okay, are we done yet? No. So this is where you find it, right? When you find that keynote bit ID. What if you didn't find it? It's not in the first node in that slot. Well, then you have to go searching through all the rest in the linked list, right? If there's any. So you do else. In that else statement, you have a collision again. Search remove item in the chain list, right? So I'm gonna save the current pointer to keynote.next. And I'm searching my current keynote as a previous node. Okay, you will see why I'm doing this. So if the next node is not empty, and if the next node bit ID is equal to bit ID, remember equal is comparison, that single equal is assignment, right? So deleting, so I search the next node until I find it. If I find it, what do I do? Okay, so let's look at this picture. Say I found 44. You cannot just delete 44 because there's 55 after it. So you have to access its parent and set the parents next to its next and delete it. Okay. Okay. So if I find it, so pre is the parent, right? Pre next equal to current dot next. So now I'm going to delete current now by say set to none and return. Okay. So this is the second condition where it's in the you have a collision and that node is not the last node. Okay. So that will take care of that. Now don't forget, all right? If now then you're gonna just keep searching. Pre is current. The current becomes the pre, and the current become current dot next. So you keep advancing this pointer. There are two pointers. One is the parent, one is self, and you just move after that. So pre and current. So basically, the pre goes to 77 first, and current is 44, and current on the next round, the current pre is 44, current is 55. So there's something more here. All right. So that's that. That's for deletion. Now, of course, if everything you searched have no Dutch node, right? If that's the case, then you just print something says, sorry, no such node exists in the hash table. Okay, so that will take care of everything. If there's none or there's no key means it's empty node. Okay, so I'm gonna leave the search for you to figure out. It's very similar to the delete. If you can find delete, you can search. Finally, I'm gonna run it. So basically load bits, exception occurred, list the index of the range, display of bits. All right, so did I implement, let's see, which one? Yeah, it must be that thing in the insert, right? So you have a try catch block in this thing? No, we don't have it. Yeah. Let's see, self hash in bit ID. No problem. So keynote is self data key, not keynote. Keynote is not the same thing, right? Okay, I'm gonna do not keynote. Same thing. Keynote is node bit key equal to key. Okay. Not key. No dot key bit and next is none. No problem. Self data key equal to all right. And else while keynote dot next. Okay. Sorry about that. Keynote next. And that. So that's insertion and print all, remove, search, and is there anything load bits? This index of range. So the default is a December CSV. If you want to load more data, you can load this guy, right? So load bits, display all bits. Because I didn't load. Exit. So let me just run this manually. Python main.py -p is ebit non-sales.csv load bits, range. Let's see, load bits. Table. Title and insert. Okay, let me print a bit. Right? Let me just do a print bit. Run again. That's a bit. ID, title, font, amount. Okay. And so that must be in the insert, right? So let's go back to the insert function again. Take a look here. So what do you do? Well, let's print some keys. Oh, okay. This is a good chance for debugging, right? Self data key. So the self data initially, what's initially is empty. And so if you get the key, the data is empty, it's gonna be a problem, right? Right. So you have to initialize this. Here's the problem. If it's empty, you get an index that's out of. So you have to initialize to none for everything in range of default size. So basically, this is to using list comprehension. I'm going to initialize everything to none. So at least you have that amount. If you do that, then that should work. So load all the bits. See, it's already loaded, right? And display all the bits. Attribute bit. Come on. So yeah, you can see it's we can get rid of the print function now. And it's line 99. let's see, 99 node bit. We don't need that. Okay, and then try it again. Display object. Oh, node object not attribute bid. Oh, okay. So that's in line 102. 102. Temp dot bid. Oh, yeah. Right. In a print function, come the node. If you look at the node, you can see that has key value and next, right? Key value should be node dot value then, right? So node dot value. Wait, how to define? How is the node defined? Oh, the value. Yes, that's right. Value and next. So it's a value, right? 1, 2. That's right. So now I can find a bid. Let's say 98177, and it's not searched. The search function. Oh, I haven't implemented search function. Yeah, that's right. I'm gonna do a remove function. 98177. All right. Yeah. So you have to go back to the node, which is the line 117. Sorry about that. It should be a bid. To value. Since I have the bid all over the place, I'm going to change this node, to bid. Okay. So the value is the bid. So now all I need to do is change this print function, print all function, print bid. Okay. So I'm using a bid, not a value. You have to use a value. All right. So try it again. Load our bid, print our function, remove a function, 98177. And yes, it's removed. Now I cannot find this, if you display of this, you can see 98177 is not there. Okay, so that's it. Okay, so you implement the search and complete all the data, and just be careful. If you follow my video, the self dot value should be self dot bid, right? Because otherwise, every time I refer to the bid, you should change the value. Other than that, that's good. All right, thank you, and good luck.